Hi, is this your poster?
Yeah, there's a friend line.
So yeah, here, the beginning of network performance. We had a very nice discussion. Basically, there's a bunch of guys what we want to do is obtain their insights to output that the layers get structure. Yeah, right. Especially the structures layer. Yeah. Like the radiation patterns.
Actually, yeah, so for your stack, so like at this phi level, like what kind of, what's like the output of like say, what level of the stack?
All of that is captured here.
Okay.
So this is all the
okay.
So what you do is in the network system of the simulator, you create a structure map where you basically take, let's say, an R value that you can simply compute based on chart models, based on you offline in MATLAB link level simulator with basic codes and all this, you generate some performance curves and you then use some mathematical formulas to bring them back here in the right way. Look at the you know, so it's not that we're not doing that right now. We're abstracting, and that's the fundamental issue, because we're like, okay, we've done that in LTE, but we're doing that, you always have your and we're creating this MATLAB level curve, but with millimeter wave, with minus systems, and the animal is a different game. So we want that will be one of the most important discussions.
So I'm wondering if like there'd be a good opportunity for collaboration. So we are like pretty close.
Yeah, so right now,
The question is how to investigate. One obvious thing is just to weigh the weigh each individual point and measure it, right? But is it optimal? No, it's not optimal. So this problem was introduced in 1960 by Shapiro's mathematician information theory, and it's still open problem. No one knows what's the optimal except for the case that there is only one coin of non-zero weight. That special case, you can always do bisection and it is an optimal algorithm, meaning that suppose you have only one coin of non-zero weight and the rest are all zero weight, right? In that case, what yeah, what do we do? We take an arbitrary half of the coins, weight them, and if it's 0, then you know that the weight of all of them is 0. If it's not 0, then you again take an arbitrary another half of that, and then weigh that, and you continue this process until you find that coin which has none.
Hey Chris. Chris.
Then the problem becomes non-trivial.
Yeah.
And this is exactly the special case that you focus on. Because we realize that this localization problem is basically the same problem as this coordination. Think of the sectors in yourself, which are sectors, as points. And the number of users that you have, it shows the number of wireless that we have in each of them, the weight of that sector. Now localization is when you want to look at the base station once you weight it. So it's the same as finding the base of each of the sectors based on the number of users. As long as I can solve that problem, I have been able to solve this problem. And James, that problem of coin being here is activating those particular sectors. As long as I can activate, for example, this sector together, it weighing these 2 points together. And this is exactly what we can do just because of meter weight, because there was no concept of beam alignment like this before for these omnidirectional antennas. But now, because of this beam alignment, you can actually choose any particular substance that you want, activate it at any time that you want, and look at the number of axes that you get, ACK messages that you get. And those ACK messages give you a quantity, which is exactly like the weight of this total weight of this sector. Now thinking of these 2 problems like this, you can use whatever was known for this coin bank problem, which of 60 years, the best thing known was called nested strategies. They have a very particular property, which is very simple. They're very simple to design, very simple to analyze, and apparently very efficient. But mostly in worst case scenario. Worst case means that you want to minimize the maximum number of tests or weights that you require in order to find all these, the weights of all these coins, right? But we are not interested in worst case scenario because in communication mostly whatever we're doing, we're going to do it again and again and again. For example, if I'm going to solve this localization problem for one communication session, I have to again solve this problem for the next communication session, and so on and so forth. If you're doing repeating this game, average case scenario of the problem is much more relevant compared to the worst case. In the literature, you cannot find anything like the average case, but for the worst case, these strategies were studied and shown that they are very efficient. What they do is like very simple, very similar to the white station, and they say that as long as I learn something about part of this sector, and I know that there is someone there, closer one user there, then my next test is going to be a proper subset of that region. For example, if I activate the first and I activate this region and I know that I get no ACK message, so I know that no one is here. So then I know, suppose that someone tells you at the beginning that there are 2 users in the cell. Then you will learn after this test, you will learn that 2 users are in right? Now that we know this nested property says that the next test to replicate the message must be a proper subset of these 5, 6, 7. For example, has to be 5, 6. So you activate these 2 sectors. Now what do we learn after this test? First thing, we know that one user is here. Why? Because we get only one after this activation. Also, we learned that there is one user here. Why? Because we knew that there are 2 users overall at 5 to 8. Now we know one is here, so your uncertainty region is reduced. Right? Now you know that it's between 5 and 6, and another one between 7 and 8. And now what you do again, because of this nested property, for each of these 2 regions, you have to choose a proper subset of them. For example, for this one, you choose this one, and that one, and so on. This was the best known technique for solving this problem. What we did was to create some sort of asymmetry in this sort of testing the scheme. This makes the problem harder to analyze, definitely, because this is very simple to analyze. This is a very nice property to do every time that you learn something. Your next test, next step, you just focus on a subset of that test. You're not going to test one part of this region and another part of another region randomly or in an ad hoc fashion. So this makes the analysis much simpler. And tracking the algorithm is as long as you introduce some sort of asymmetry in your scheme, like, okay, at this moment in time, go activate that sector and somewhere from other part of your region. In that case, this becomes much harder to analyze, but apparently we can gain a lot. So if you look at the average number of tests versus the number of points, what we achieve is just like what the people could achieve before this term, and we want this average number of tests to be as small as possible. And gaining 32% special. And this red one is actually an information theoretic lower bound that's very interesting, that says that there is no way that you can solve your problem with less number of tests than this red term. And it's not necessarily even achievable, so you might not even be able to design a scheme that achieves this. And we are very close basically to this one, actually less than 8.16% of information theory. Pretty much sure. Just to do one test at the beginning, so it activates all sectors based on particular active message. You learn that the total one test blue here is the radiation. This is
Where is MATLAB?
we cannot
cover a lot of
The channel model is all comes from the NYU measurements of the gigahertz. Then we plug in the new radio standardization parameters that, as you may see here, this is just a selection of them. The kind of spacing, the frequency diversity scheme, the number of SS blocks in a burst, the periodicity of the bursts within the frame, the beamforming architecture, analog, digital or hybrid, the antenna configuration, so number of antenna elements in the array, and also we try possible values of density. And then we run the simulations over in MATLAB, and we try to estimate accuracy, overhead, and reactiveness performance.
That's what I'm done. Hi.
Hi.
We're doing a YouTube live stream. Would you mind giving a brief?
So here we are trying to see how the initial access can be improved by complying with the free GPP new radio standardization that is being developed. The main idea is that there are SS bursts, and each one of them is composed of multiple SS blocks, which include primary synchronization signals and secondary synchronization signals to estimate the channel and select the best beam to be configured in order to make the endpoints communicate. And to do so, there are many possible options for the base station and the user. One option is to have a standalone architecture in which they just rely on the millimeter wave spectrum, or they can implement some sort of multi-connectivity, so having a fallback to LTE for the control plane management. Moreover, we may have a downlink-based architecture, so the base station sends pilot and the users perform measurements, or vice versa, an uplink architecture. As I was mentioning, there are plenty of parameters to be configured and tuned, such as the beamforming architecture or the number of bursts of blocks in a burst. And our goal here is to perform an exhaustive comparison among all possible combinations of parameters and provide guidelines on how to best configure the initial access strategy. From our results, we are showing that the accuracy is influenced by the base station density, the antenna configuration, because if we have more antenna elements, we may steer narrower beams and achieve higher beamforming gains, and also according to the frequency diversity scheme, so the possibility of repeating the SS block multiple times up to completing up to consuming all the resources available in the whole bandwidth, that here is set to 400 megahertz. Of course, there is a trade-off in terms of reactiveness, because for the reactiveness we may want to have wide beams in order to cover the whole angular space with a smaller number of SS blocks in the burst. And also the reactiveness can be improved by considering digital architecture, so that we can steer multiple beams simultaneously, and also by increasing the number of SS blocks within one burst. Again, this will have a negative impact in terms of overhead, because we are using more time and frequency resources for the control plane management rather than for the data plane. But still, we can improve accuracy and reactiveness. And so our main result, our main conclusion is that we would like to complete the angular scan within one single SS burst, and this can be done by configuring properly the beamforming architecture, the SS block configuration, and the antenna management, the antenna panel, the antenna configuration.
Thank you.
Well, that particular example was 2-inch aperture. Yeah. So,
yeah, this one's less crowded.
Somehow in 3GPP
Oh, we've already got this one.
You already got this one?
Yeah, this was your last.
Or we can go there
so we're
first.
at standard, I guess that's the reason.
Call this one?
Okay, yes. So that was working with so this is related to the work that they did. This is related to more users and that's an extension.
Hi.
Hi.
We're doing a YouTube live stream. Would you mind giving us a short presentation on what you got here?
Sure. Okay. So the problem that we're addressing here is the case of integrated access and backhaul for millimeter wave networks. So the issue is that with microwave networks, we have very few access points, so we can afford to have fiber optic to every single access point. But in millimeter wave, since we're expecting to have a lot of different access points, we will have to use the same band of frequencies to transmit from the base station to the access points and from the access point to the users. So what we're doing here is optimizing the allocation of resources between the backhaul link and the forwarding link to the users, as well as the caching of information in the access points. So the second characteristic that we're exploiting is that we usually have some sort of idea of what the users might request in a short time frame. So what we're going to do is we're going to cache some of the files which we expect the users to request in the access point in advance, beforehand, so that we don't have to make a big burst of traffic whenever the user requests a specific file. So we are using a proactive caching model, which means that in every time slot we cache some fraction from each file based on our estimation of the possible request for the future, and that information remains only valid for a limited number of time slots, capital T time slots. So whatever I cache now will become will expire after capital T time slots. So the idea here is that we're optimizing the fraction of each file that will be cached, as well as the bandwidth allocation between the backhaul and access lanes. So that's the first part of the project. These plots actually are wrong, sorry, because there was a printing error. The actual correct plots, you can see anyways, there was some sort of printing error. The PDF looks good, but the printer did wrong. Now that was the first part of the project. The second part of the project was looking at how we can re-encode the information in this relay node, in the access point. So the idea is that the base station and the relay station, or the access point, are going to be fixed. So there's going to be a good channel between them. And since we're doing this caching, there is going to be a lot of information transfer between these two. Now, with a good channel and a lot of information, we want to minimize the amount of parity that we send. So we're going to use a very high rate code to transfer this information. However, when the users request information, we need to forward that information to the users, and we will most likely require lower rate codes, actually more parity, in order to correct the errors that might happen in this other channel. Now, what can we do in order to minimize the frame error rate, to maximize the overall data rate? So the first thing and the best thing that we can do in terms of performance is do decode and forward. So we just decode whatever we receive from the base station, we re-encode it with a different code, and we forward it to the users. But maybe the data processing required for the decode and forward is too much, so we're going to explore other alternatives, which are obviously going to perform worse, but we will reduce the amount of power or computations required. Explore other alternatives for doing this forwarding of the information. And then what we can try, the basic one, will be amplify and forward, where we just amplify whatever we receive. Actually, this plot that I show here, we're not just amplifying, we're rounding it, and then generating additional parity for those rounded values, and then forwarding everything, the original parity and the additional parity generated based on possibly erroneous values. And then the user would have to decode the first code to get the possibly erroneous values, whatever this guy received, and then decode the second code to recover the original information. That would be this other curve. So decode and forward would be this curve, where we're showing frame error rate versus SNR. Amplify and forward, or what I'm calling round and forward, would be the second curve, which is worse. And despite I haven't been able to achieve better results yet, I'm hoping that I will be able to achieve a curve in between by doing something which I have previously studied, which is using eraser parity bits. So using an eraser code across different code words at this level, and then the relay station will be able to decode this eraser code across the code words so as to improve its estimation of these bits. Then it can basically re-encode those bits, which are hopefully better, and forward them to the users. So that's basically 2 cents. All
right, great. Thank you. Hi. Sure.
So thank you. My name is Dr. Arjuna Madanayake from the University of Akron. So I'll be presenting some work on the co-design of radio frequency front ends and order n complexity approximate discrete Fourier transforms for software-defined radio applications. And this work is a collaboration by myself with Dr. Renato Sintra, Dr. Dimitri Saiko-Joule from Thailand, and Dr. Pilastotsky in Canada. Okay. All right. So what are we trying to do? We are looking at the problem of designing an optimal software-defined radio, but we are taking a top-down approach where we look at the microwave front ends, the performance of the software-defined radio part, the algorithms as a total entity, and trying to optimize the performance across all parameters. So, as an example, we know that the fast Fourier transform, or FFT, is an algorithm for implementing a discrete Fourier transform, and is a very common building block of pretty much all software-defined radios. So, using an FFT as an example, I'll explain to you the approach. Okay, so an FFT is a fast algorithm for implementing a discrete Fourier transform, or DFT. So a DFT, if you want to build directly in hardware, will require about n squared multipliers for an endpoint transform, and an FFT reduces that from n squared down to about n log n. So it turns out that by allowing a little bit of error in the computation of the FFT using approximate computing, you can get rid of this n log n bound and make it smaller. We can make it order n. So that reduction of a factor of log n becomes very significant for large n. For example, for 1024 point transforms, the factor of log n is 10 times. You can make it 10 times smaller. So when you make it 10 times smaller, because it's an approximation, what happens is that your frequency responses of your discrete Fourier transform are not that good. There is some error. We call it some imperfections. So we quantify imperfections. So that's the price we pay for getting something that's more than 10 times lower in power consumption. Okay. So given the imperfections, the question is, can we now quantify that and redesign our front end so that these imperfections actually don't have much of a role to play in the final performance? So what we do is we optimize the low noise amplifier LNA using wideband matching and noise matching to get best sensitivity. Then we include some tunable filters for optimally removing interference, right? So we optimize all the microwave front ends as much as possible, and then we estimate for that optimum front end what's the bit error. So once we know that what the best we could get from this transceiver, the analog part, then we can go back to the software-defined radio algorithm and allow just the right amount of error so that you can get the best power consumption and complexity in the digital part while not getting any hit in the performance of the total system. So that's a broad optimization using order n complexity approximations of the discrete Fourier transform to get overall lowest power consumption chip area without much hit in the performance of the total system. Thank you very much.
Thank you.
So you are going to edit this in a short way. How are you going to put this?
No, it's live streaming, so
Okay.
it's just a really long video of us walking around and.
Oh, okay. Okay.
Going at the same direction with a different phase. So that they want to Yes.
Hi, we're doing a live stream on YouTube. Would you mind giving us a short presentation of what you have here?
Okay, sure.
Thanks.
So in here we are considering we want to design a multi-part links network so that to improve the reliability of the system network. Because we know the system network is very vulnerable to the blockage and the orientation. For example, if the human stand between these two links, the throughput will drop to 400 megabits per second. If the device rotates by 100 degrees, is not perfectly aligned with this point, the throughput also drops. So one feasible solution is to fall back to a sub-60 band. That means if the 60 link becomes worse, we should use the Wi-Fi transmission. And there's two existing design related to this idea. One is the fast station transfer. That's to move the Wi-Fi, the link to the Wi-Fi link with the system to the brick. But this design scheme is repetitive, and there's maybe some very short transitions which the link is stored. And the other is the multi-part TCP. But this will require the server-side application, and we only work for TCP, reserved for the radio streaming applications like the UDP. So our basic idea is to propose a multi-link transmission framework. So it will virtualize the Wi-Fi and Wi-Fi interface into one. So the basic idea is to split the packets coming from the IP layers and transmit them through the Wi-Fi and Wi-Fi link at the same time, and we assemble them on the access point side, and then send them through the Ethernet. The benefit is that we can get a higher bill rate and also better link quality and it's also transparent to the upper link application, so that it doesn't require any modification of the IP layer. In order to implement this framework, there's several technical challenges there. One thing is you need to deal with 20 times rate difference between these two interfaces, and which will cause the packet out of orders. So we need to reorder the packet at the receiver side inside the virtual link. Besides, we also need to deal with the link reliability difference, because the Wi-Fi is more reliable than Wi-Fi, and we think the Wi-Fi should be transmitted part of the Wi-Fi lost packet, so that this bit rate won't be reduced too much if some packets are lost. And also, because these two links they have very different coverage, and in the multi-AP scenario, then the client moves from one access point to the other access point. In order to keep this link connected, it's better to move one link before the others, so that we need to have also need to have a mechanism to deal with the application with respect to different access points. And on top of that, we can have several different research problems here. One is we need to design different GPU scheduler. For example, for the real-time condensed video, we can use the SVC coding that will encode a video frame into a low-quality base frame and a detail frame. And the low-quality base frame will be sent over Wi-Fi, which is reliable, and the detail frame will be sent over the 60 link. Even though some packets over the 60 links may be lost, but the users can still see the video content because the base frame will be received. And another idea can be the energy efficient networking. That's for different applications. We can exactly turn off some interface. For example, for the web browsing, which doesn't require very heavy data transmission, and then we can just turn off the CGS links, and then just use Wi-Fi to transmit, which will save the energy. And another interesting opportunity under this framework is that because the virtual link sits on top of the AP, so it can see the physical layer information from the link. And we can use this information to design some smart algorithm to decide which package is sent over which link. And then, for example, we can use the physical information to predict how the Wi-Fi channel is going to change, and then to determine what's the required rate for each of the interviews. And that's the basic idea.
Great, thank you.
Which one? This one?
Sure.
The game is too less than that. It's like the only we still have a couple of issues
Go, I don't know where.
It's more like
To go.
Alright. Great. Here?
Yeah. The beam is just like omni. So no matter what you do, it's omni.
Exactly. Like theoretically, you can get a nice multi-lobe pattern that looks like this, but when you look at actual measurements, actual patterns, they look like they're like 60-degree beam width or so. So it's not very likely that you'll be able to design those nicely separated multiple main lobes that we're looking into. Yes, this is MATLAB's. Yeah, all of those simulations and the antenna patterns are done on MATLAB's phased array antenna toolbox. You're welcome, thank you.
Hi.
Hey.
We're doing a YouTube live stream. Would you mind giving us a short presentation of what you got here?
Yeah, sure. So what we are trying to do here is to borrow some of the concepts of digital beamforming and apply them into analog beamforming. So in digital beamforming, what you do is you transmit some pilots, and using those pilots you measure the channel so that you design your pre-coders accordingly. So that channel that you measure doesn't really give you a direction, it gives you a combination of several multi-path components. But what we do generally in analog beamforming, we simply design a codebook. We do a codebook-based approach, meaning that we design a pattern that is looking into a direction, and then we simply switch that direction at each time slot to find the best direction. So what we're trying to do here is, what if instead of finding the best direction, what if we try to find a combination of several directions? Meaning that we don't look into just the line of sight, but what if those line of sight and maybe the first order reflection paths and the second order reflection paths adapt constructively? What happens in that case? So to be able to do that, we design a multi-main lobe antenna pattern. We allocate some of our antennas to design one of the main lobes and some other antennas to design the second main lobe, and so on. And a quick takeaway from that would be this figure over here. So we look into what happens if we transmit or if we receive through just the best direction. And this is the median SNR that we can get if we utilize only the best direction. And if we look at the best two clusters, the best two angle of arrival directions, you can see that we can improve our median SNR quite a bit. And if we look at the best three clusters, we can further improve our SNR. But if we look further more into more clusters, that goes back down, simply because this is the 3GPP model. Apparently in this model there were like 3 significant clusters, and the 4th cluster had like significantly lower power compared to the other clusters. So when you start to allocate some of your antennas to create a 4th main lobe, you're simply wasting your power and not gaining really from designing that main lobe.
Great.
So yeah, that is it.
Thank you.
What else?
Did you get, which ones did you get over there?
The last one at the corner. Want to do that?
Sure.
So that's not going to work for me. And so what we do though is there's a method called transformation optics, which is essentially conformal mapping applied to material parameters and electromagnetics. So what we do is we start with a hypothetical design, which is we know that this permittivity profile gives us a radiation pattern that we like, but we would like it to be flat. So we prescribe a coordinate transformation. And here I'm just actually saying that x is x and z is z, but y I'm going to compress it vertically. So this is my coordinate transformation. And I basically compute the Jacobian of this coordinate transformation. I crank it through the transformation on this algorithm, and out pops a new permittivity profile. And that's what you see over there. The original profile was 2 in the middle and 1 at the edge. After a compression of a factor of 6, we're now at 12 in the middle and 1 at the edge. 12 is pretty close to 11.8, so that's why we picked silicon. And now we go into the clean room, and we have this map, which is our design. Go into the clean room and we etch these. And we've just begun characterizing our repeatability of this process. So here's some histograms of 40 samples, all designed to be etched to a particular value. And our standard deviations are, if we were targeting a permittivity of 8.3, we got a mean of 8.27 and a standard deviation of 0.13. So we're dialed in pretty well. We can get a little better. But now we can say that, yes, in fact, when it needs to be 12 there and 6 here, we can do that. So that's the lens itself. Now you have to make that with a feed network. And the feed network is really, so right here you're going to have, I'll mention one thing, this is the matching label that I'm showing here. So I don't know if it's obvious, but right here the permittivity is 1. Notice that that's green and not dark blue. So this permittivity is actually 6. And if you have a feed down here, and it's coming from air has a permittivity of 1, and now you're getting a permittivity of 6, you have an impedance mismatch. So this is the impedance of free space, and this is a different impedance. And so you actually need to do impedance matching on the surface. If you're familiar with optics and lenses, they have something called an anti-reflection coating, AR coating, so that's essentially what we're talking about. This is the microwave equivalent of an AR coating. So you do that, and then there's a little spacer. The overall thickness of the particular lens that we're showing here, the lens itself is 7 millimeters thick, and the feed elements are 6.5 millimeters below the surface. So it's a 1.3 centimeter antenna, and it's 2 inches in diameter. So the thickness of it can be compressed, but what happens, notice that we started at permittivity of 2, we compressed by a factor of 6 and ended up with a permittivity of 12. So you can just basically multiply your maximum permittivity by your compression ratio. So if we wanted to compress this even thinner, we'd have to put a higher dielectric constant. So anyway, we've been developing this design method and fabrication. We're in the process of building up our full-up demonstration lens. And I think the lowest hanging fruit for us is this angle of arrival spectrum sensor, where we're just going to put some energy detectors on the bottom. But we just started a project with a company that's interested in doing full-up transceivers for SATCOM purposes. And so we'll be actually prototyping full basically equivalent access points.
Okay.
How big is the feed network going to be?
Go back to there.
I see that, you know, they're
Down here.
All right. Hello. You already did it, or? Okay. Sure.
For when cells get so small that they're just access points too dense to transfer fiber. So mesh network doesn't provide enough measures. And solutions things that don't have wire. Various constraints we formulate the optimal working and application but formulation is that it goes up. It's exponential. The number of variables that so we get some solutions that keep building which we show that scale easily with problem size, and some networks looking at several grams, like a very large network can lower number of hash within a minute, and show that you can get 20% of the nominal link rate as throughput to each case.
That is true.
Great, thank you.
What else? I don't know. I guess we're finished.
All right.
Okay. You can't stop?
Yeah.